Welcome back to another training video using the UK Electrical Simulator. In the last video, we built a complete off-grid electrical system, but we kept it at a fairly high level. We showed how the main components connect together, including the solar panels, charge controllers, batteries, inverter charger, generator, mini consumer unit, and AC loads. In this video, we're going to slow things down and start looking at each part of the system in more detail. We'll begin with the solar panel component because this is one of the main sources of energy in many off-grid systems. Solar panels come in many different sizes and ratings. In the simulator, we have several example panel models, such as 300, 350, 450, and 500 watt modules. Each model has its own electrical characteristics, including rated power, VMP, IMP, VOC, and ISC. The rated power tells us the approximate maximum output of the panel under ideal test conditions. For example, a 300 watt panel can produce up to around 300 watts, but only when sunlight and conditions are suitable. VMP means voltage at maximum power. This is the voltage the panel is expected to operate at when it is producing its best working output. IMP means current at maximum power. This is the current the panel can deliver at that maximum power point. We also have VOC, which means open circuit voltage. This is the voltage measured when the panel is not connected to a load or charge controller. This value is very important because open circuit voltage is usually higher than the normal working voltage, and it must not exceed the maximum input voltage of the charge controller. Finally, ISC means short circuit current. This is the current that could flow if the panel output was shorted under test conditions. We use this value when checking cable sizes, protection, connectors, and charge controller limits. In the real world, solar panel output changes depending on sunlight, shading, temperature, panel angle, and the type of charge controller being used. In the simulator, we simplify this using a sun percentage slider. When the sun percentage is reduced, the panel current reduces. When the sun level is increased, the panel can produce more current. We can use a single solar panel on its own, or we can connect multiple panels together. This is where we need to understand the difference between series and parallel connections. When solar panels are connected in series, the voltage increases, but the current stays roughly the same. So if we connect two panels in series, the total voltage is added together. This can be useful when we need a higher input voltage for a solar charge controller. When solar panels are connected in parallel, the voltage stays roughly the same, but the current increases. So if we connect two panels in parallel, the current is added together. This can be useful when we want more charging current into the system. But we have to be careful. Too much voltage can damage the charge controller, and too much current can overload cables, connectors, or protective devices. So whenever panels are connected in series or parallel, we need to check the total voltage, total current, cable size, and the maximum input ratings of the solar charge controller. A simple way to remember is that series increases voltage, whereas parallel increases current. Now let's take this theory into the simulator. On the workspace, we have 6 solar panels. If we connect the meter probes to the first panel, we can see an open circuit voltage reading of around 50 volts. We can also confirm this value by clicking the information button on the panel component. We can also change the solar panel name and model by double-clicking and choosing a different option. Now remove the B probe from the negative terminal and connect the first panel to the second panel in series. To do this, we connect the negative terminal of the first panel to the positive terminal of the second panel. We have now wired the first 2 solar panels in series. If we place probe B on the negative terminal of the second panel, we can now see a reading of around 100 volts. This confirms what we said earlier. When panels are wired in series, the voltage increases. Let's quickly connect all 6 panels in series and take another meter reading by placing probe B on the final negative terminal. We now see a voltage of around 300 volts. The problem with this setup is that we may not have a solar charge controller that can safely handle 300 volts on its PV input. We can check this by opening the Solar Charge Controller Models table from the Resources drop-down menu. In the table, we can see that even the larger MPPT 250/100 model has a maximum PV open circuit voltage of 250 volts. Our 6-panel series string is producing around 300 volts, so this arrangement is not suitable for this type of small off-grid charge controller. Small off-grid charge controllers normally work with relatively low PV string voltages, such as 75, 100, 150 or 250 volts. Higher voltage PV systems, especially those approaching 600 volts or 1000 volts DC, are usually handled by specialist hybrid inverters, grid-tied inverters or commercial PV equipment, rather than basic domestic off-grid charge controllers. To reduce the voltage in our solar panel system, we need to wire the panels differently. In this example, our solar charge controller is modelled as an MPPT150/70. Even though this controller is rated up to 150 volts, we should not design the solar string to sit right on that limit. The 150 volts is the maximum permitted open circuit voltage, not the target working voltage. In a real installation, cold weather can increase the panel voltage, so the total string VOC must remain safely below the charge controller's maximum PV input voltage. For a 150/70 controller, we want a more practical open circuit voltage somewhere around 70 to 120 volts. We can achieve this by wiring the panels in a series parallel arrangement. Instead of one long string of 6 panels, we can create 3 strings of 2 panels in series and then connect those 3 strings together in parallel. This gives us the voltage of 2 panels in series but increases the available current by having 3 strings working together. Always remember, series increases voltage, whereas parallel increases current. Let's rewire the array. First, remove the wire links between panels 2 and 3 and also between panels 4 and 5. This separates the 6-panel string into 3 smaller strings, each made up of 2 panels in series. Now connect the 3 string positives together at the positive connector and connect the 3 string negatives together at the negative connector. In other words, connect positive to positive and negative to negative. Now place the meter probes onto the final positive and negative connectors. We can see the voltage is now around 100 volts. That means we have successfully wired 6 solar panels while keeping the voltage at a much more manageable level for our 150 volt solar charge controller. This is the main design point for this video. We do not simply connect as many panels as possible in one long series string. We need to check the total open circuit voltage and make sure it stays within the charge controller's maximum input rating. In this example, 6 panels in series gave us around 300 volts, which was too high, but 3 strings of 2 panels in series gave us around 100 volts, which is far more suitable for the controller we are using. I hope you've enjoyed this video explaining how solar panel wiring affects voltage, and how series and parallel arrangements can be used to keep the PV input voltage at a safe and practical level. In the next video, we'll look more closely at current flow and see how the current changes when solar panels are connected in series and in parallel. Please like, subscribe, and leave a comment below.